things to consider analytically that are important when we're doing these kind of operations. Now, really, we have to cover this, because I haven't covered much MATLAB, and I don't know, is the other class right now covering MATLAB routinely or not? Anybody know? Usually you get MATLAB assignments in this course. You get a series of them. What the problem is with MATLAB, most people don't know MATLAB that well. And so it is assumed that you can pick it up on your own. Now, I know you've had MATLAB you can pick up on your own. It's not that hard, but the thing is, it does take time. It's intuitive to a point, but it's not something you're going to learn how to use overnight. So I got to take you through some MATLAB stuff, a bunch of you people. And this should help you. MATLAB's used by everybody, everywhere. One of the problems I have with this system is they don't have the easy plug-in. All right, where's the... What's that?
It looks like there's a corner missing on your ThinkPad.
Yeah, let's go through the board sideways. It suffered a lot. Say one thing, if you ever load a laptop and baggage here, here's a piece of advice. Make sure it's well padded.
Yeah.
You ever watch them handle baggage in the airport? They toss the bags.
Yeah.
Doesn't work well with something like that. What's that?
I said, or it's either. Yeah, United Briggs Guitars. They broke the guy's guitar, and the real reason the song got written was they refused to give him like a penny for it. So then he went and wrote the song.
Yeah. I mean, it was like a $2,000 guitar,
Yeah.
so.
You break my stuff, it's okay as long as you pay for it.
You did pretty well out of that.
All right. Now, guys, I gave you a MATLAB. This is going to be due on Friday. I need you to make sure you do this and pay attention to this lecture. I know it's for thin. 2, 4, 6, 8, 10, 12, 14, 15 people. I'm going to try to help you. If you have questions, ask me those questions. Now, first thing I need to ask you is how many people have done anything with MATLAB by themselves from scratch? Just a show of hands. How many of you use MATLAB in any way? Let's try that approach, because I know a lot of you have. If you copied code and used that, you probably have some idea of what's going on, but not a good chunk of what's going on. If you brought your laptops, please get MATLAB up and running if you have it available to you. So I'm going to try to help you with this as best I can. Now, with MATLAB, how many have MATLAB up and running right here? One. What? Octave's fine too. But MATLAB or Octave is the free one you can download for nothing. And I suggest if you want something free, use Octave. It's slower, doesn't have all the toolboxes, but it still does work. And you'll be surprised at how useful it is. This is MATLAB. Now with MATLAB, you have something that you can get, it's called, and you can open files or open things in M files or scripts. When you go open, like you can open anything or you can create a new file. I've got a couple files open here. I can easily open another one. I'm gonna just start from scratch. So this is a new window. It's gonna be in your editor. If you don't know how to do it, you got MATLAB open, put your hand up. But the only thing you're gonna do is open a new file. You'll notice it's called Untitled 2. Can you all see that in class? We'll name this in a second. So what I normally do, and I'm not saying you have to do this, but MATLAB holds things in memory. So I always put clear all, then close all, and then CLC. You don't have to do that. The clear all gets rid of everything in memory. The close all close windows that are open at the time. And the CLC simply takes this window over here that's really a command window, it's called. Like here, if I tap in here, you'll see it just go down. If I want to know what's my directory is, I can type DIR, and it's going to give me a list of all the files I have access to in that directory. But what happens really is, the thing you want to worry about is going over here. This is going to be something called a script that you can run and run again. You see that run bar right here? That arrow? I can rerun this as many times as I want. Now, after you do that, normally the next thing you do is define anything that are going to be constants throughout your program. For instance, if it was an electromagnetics problem, you might have mu0 is 4 pi times 10 to the minus 7th. C is 3 times 10 to the 8th meters per second. All the constants. Now, pi is self-defined. You just have to type pi, and it's self-defined in here. But a lot of things aren't. Just remember that. So anything you're going to use over and over again, a constant, type there so you don't have to type out the whole thing every time. Then you come to, and I'm going to show you what we're doing here, which is windowing. I'm going to start with a frequency called a sampling frequency I'm going to use of 1,000 hertz. So that's my sampling frequency, and the sampling period, therefore, is equal to 1 over 1,000. I'll tell you more about that in a second. Really what I'm doing, I can just do this. I'm typing it out all for you from scratch, but let me just copy this and I'll explain what I'm doing. I was going to type out everything, but I'll just copy that. I've got an actual frequency that a cosine waveform is going to operate on at 6.5 hertz. My sampling frequency that I had here is actually shown below there, and it's equal to 1,000. It means it's sampling at 1/1000th of a second. It's sampling the signal. Now remember with windowing, as the signal comes back with radar at least, as it's coming back, you're sampling that signal that's returning at a certain rate. And you're going to sample it for a certain length of time too. Are you with me on this? Now, the number of samples I'm going to take is going to be n. So it's going to be 1/1000 times 1,000, or 1 second is the total interval that I'm sampling. You follow me on that? Everybody? Something I should say, anytime I put a semicolon, when I put F0 is 6.5 semicolon, what that does is prevent that from reappearing in the command window. It'll prevent that from showing up. So it doesn't just fill the command window with nonsense. How many knew that, by the way? Hopefully most of you will catch on. This is the thing is I'm showing you are things I would want to know if I was sitting where you were. Because a lot of profs aren't going to tell you this stuff. They're going to assume you're going to pick it up on your own. And frankly, sometimes it's frustrating. The next thing I'm doing here, something else, anytime you put that semicolon there, I can put another feature right next to it to find something. I don't have to put it in the next line below. So that semicolon also allows me to put other information. Here I just put t is equal to 1 over the actual sampling frequency right there. Now n, now listen to me now, n is going to be the number of samples. This small n is going to be an index that I'm using that defines the sample. So I know I have 1,000 samples, but I'm going to start labeling small n from 0, that's the beginning of this counter, out to n minus 1. Because 0 would be the first sample, n minus 1 would be the last. Follow me on this? In other words, it would be from 0 to 999. That's 1,000 samples. You all with me, class? I'm trying to show you things. Hopefully it will be useful in future classes, not just mine. Now I'm defining a waveform. Now what I'm going to tell you is this. What I'm trying to do is show you windowing. This is a waveform. It's a cosine waveform. If I send out a radar signal, this is scaled way down in frequency. I don't want to try to get up there in gigahertz range stuff yet. I want to scale everything way back. If I send out a signal, a radar signal, the return signal would have the same frequency as the original signal, plus possibly a Doppler shift that would be very small. But nevertheless, it would look basically identical to the signal I transmitted. All right, class? Remember, when I transmit a signal, it's on for a certain length of time at a very high frequency, then there's dead. It's nothing. Then it's on again, and you listen for the reflections. And I'm just showing you this to demonstrate the windows, the Hamming window and Hamming windows, a few others that I've done. So this is really the signal. Now you'll notice here, for this one, I'm defining something called time, where it's n, that's from 0 to 999, or it's 1,000, and it's going to be times t, where t is going to be the sampling interval. So I'm sampling this cosine waveform, think of it as it comes back, every 1/1000th of a second. Please take a look at that. Does everybody follow me what I'm doing? I'm assuming this cosine waveform is something that's going to be returning, and now I'm sampling at a rate of 1/1000th of a hertz. But the actual oscillations in the cosine are 6.5 hertz. So that means I'm sampling it extremely fast compared to the variations. Does you follow me on that? And you can make the argument that the change in the value of that cosine waveform from one sample to the next sample is small. Now, do you remember when we did the comparison of the actual Fourier transform to the adjusted DFT? Y'all remember that? One of the preconditions for that comparison working was a very high sample rate. Are you with me, class? Everybody with me? Don't worry, I'll give you this code. You don't have to worry about it. I'll give you all the codes. Trust me, I'm not worried about that. I want you to have them. They'll be helpful, but I need to take you through them. Now, after that, when I do this, remember I said with the window, you're going to sample a very small portion of all the signal that returns, right? So I'm sampling over a length of 1 second. I'm sampling 1,000 samples, and I'm assuming this cosine waveform is what I'm looking at. But now what I need to do is take a look at what it looks like in the spectral domain. So the next thing I'm going to do, I want you to pay attention to this next step. It's very, very important. And I'm going to go over here to the command window and show you some stuff too. What I'm going to do is take this cosine waveform, x. See how x is defined there? That's going to have from 0 to 999 points. Are you with me? Now please pay attention. With me? There's 1,000 points there. All right, 1,000 entries. But now I'm going to place zeros next to it. Now you see that function, zeros, 1 comma, 99, 0, 0, 0. What that means is I'm going to go ahead and everything after that is going to be zeros out to 100,000. The first 1,000 points have something going on, and then it's dead. Follow me? Now you remember what a window does. It takes a signal, a cosine waveform, and then here I'm going to use a window with a weight of 1. It's the pure rectangular window, and it just takes a portion of that, right? And there's deadness after that. Now you remember that for the DTFT? Now what we're going to do is approximate a DTFT using a DFT or an FFT by saying, I put zeros in there, right? All those zeros. Now what I'm going to do is take that, and if you look down here, that this is the function I'm going to plot these. So you see, now I'm going to say that now my transform of that in the frequency domain is an actual Fourier transform, the FFT, of this zero pattern function. Are you with me, class? Just let me take you through it. Everybody see that? FFT takes the fast Fourier transform of that. I'm going to adjust for a lot of this. I got to go back here. I don't want to keep typing all that. Then what I'm going to do is plot this. Now let me just explain. I'm going to get the plots here, and I'll explain what goes on. All right, now, you'll notice I'm not using the function plot, I'm using subplot. All right? Now, if you haven't used it, it's fine, you can look it up. You'll notice the first entry is 2. Y'all see that? That means there are going to be 2 plots included in this. They're called a subplot because there's going to be the first plot and the second one is going to be arranged under it. Now, you'll notice the next entry, 1, 1. That's like a matrix entry. You all see a subplot 2, 1, 1. It means in the first position, first column, first row, this is where that subplot's going to be. The next entry is 2, 1 down here. You all see that? It's 2, 1, 2. Well, what is 1, 2? That's the second subplot. There are only two of them. Are you with me, class? Now, what is contained in this first subplot? Well, it's going to be a plot of simply n and then x. In other words, it's simply going to be the function, the cosine function sampled over the interval of 1 second. I'm going to re-show you that, all right? Class? That's all I'm showing you there. And then I actually label this the samples and then the amplitude. So it shows the sample number. I could put it in seconds if I wanted to. It could be what? N times t would be the actual point in time, right? Because it's sampled at fs. But I'm just showing you versus n. And then the amplitude, and this is the time domain signal to be analyzed. I'm going to show you one thing with MATLAB that's nice. If you want to just execute that portion of the code, if you highlight all that and type F9, I think F9 does it on mine, it should run. I got this thing messed up. All right, now let's see. I used to be doing that. Let me see if I can do this by right-click here, evaluate selection. See that? It's supposed to be F9, and it should do it. Okay, now it showed me this part. It just showed me the signal, but it didn't show me the DTFP. All right, that's just the subplot there. In other words, that's just simply the waveform, the cosine waveform I'm evaluating through a windowing function. Next, I'm going to take a look at this now. Here, this is going to take a little explanation. In the second part, what I'm going to do, I'm going to plot the DTFT, which is this XZ pad, and I put that down there because we have zero padding. But I'm going to plot that not over the entire range of the DTFT. Listen to me now. I'm only going to plot it, if you think about it, we're sampling at a rate of 1,000 hertz, or 1/1000 of a second, right? The frequency of the cosine waveform is 6.5 hertz. Do you follow me? Now, when we actually display a DTFT adjusted with frequency, and I'll show you how to do that, we're going to get everything from 0 to 1,000 hertz, but we don't want that. What we want is something that focuses in on a range from 0 to, say, 30 hertz, something where we can take a look at where the 6.5 hertz signal is centered and how it looks. Are you with me with this, everyone, class? So we adjust for it, and what we do is this. We take a portion of the entire, remember how many samples total are there? There's 1,000 with the cosine waveform, but I zero pad it out to 100,000, right? I'm only going to take the first 1,500 points, and I'll tell you why in a second. And when I do that, take a look here. When I'm going to say bins goes from 0, this really is going to be the horizontal axis. It's like the k-axis in a DFT. That's just the number, the points you are out there in the DFT, all right? And I'll adjust for this in frequency. Work with me here and you'll see this. And then I'm going to say when I plot this, I'm only going to go for the first 1,500 entries from 0 to 1,500 as far as the K value and the value of the zero padded magnitude. In other words, my FFT only for the low frequencies. I'll show you how to adjust for frequency in 1 second. Let me make sure I get rid of this label. I want to put the bins here, and I want to put, well, oh, by the way, one thing. You see how I'm putting a percentage sign there? Anything else? What that does is comment out anything. If you want to write a comment anywhere, you just put a percentage sign. Everything after that percentage sign is a comment. That way, it will not affect the program at all. Are you with me? Please remember that. Comments are so useful when you're troubleshooting code. If you get a long code, especially with a lot of subroutines, I call them subroutines, they're really just M files here. You'll be surprised how much you forget when you start writing a really long one. You have to code, you have to write all sorts of comments. All right, now I'm going to get rid of that, and I'm also going to get rid of, let's see, I'm going to get rid of this too. Now I'm going to go ahead and run the whole thing and show you what I'm talking about. Oh, goodness. Now it's asking me what should I call it. How about I call this window 1. Looks like I call something that. How about we call it window 2. Work it out. Why is isn't solved. It's saving this in a system file. Just so, save it over here. Now, y'all see this? Class? Listen to me now. I'm using a rectangular window. I multiply that cosine waveform by just 1 over the sampling interval. Follow me? And now I'm displaying first the top part is the waveform, and you notice it's number of samples, not time. I can put it versus time. And here is just the DTFT of that in bins. Now you look at this, the bins don't mean a lot to you. What you'd like is this axis scale the frequency, wouldn't you, everybody? In order to scale it to frequency, here's what you do. You'll know that the sampling frequency is 1,000, right? And we have, and I'll show you how to do this, right here. When I took, and if I wanted the actual frequency, I could take the bins divided by the total length, or by 100,000, and multiply by the sampling frequency, and that would be the frequency. So I'm going to do this. Now watch this. You see where it says plot bins 1 1500? That's the n value from 0 to 1500. We know we have 100,000. So if I take this right here, and I go ahead and I multiply it by the sampling frequency times 1,000, and then I divide it by 10 to the 5th, because that's the actual number of total samples, right? I zeroed that out to 100,000. You with me, class? What that'll do is show me the axis in hertz, and then I can do this. I can get rid of that and put this here. Now, y'all see that in hertz? You'll notice that my frequency here is 6.5 hertz is the frequency I had for my cosine waveform. You see how it shows up as the peak? Please watch this. I'm going to show you a few other things while I'm at it. If I wanted to change that frequency up here, I can change it. Instead of 6.5, I can make it 6 hertz, right? Class? Let's see what happens. Y'all see how it moved down to 6? What about 5? And one other thing I can do, this will even make it better. This is just things I'm adding as I go. I can type down here, grid on. And what that'll do is have a rectangular grid. You can define how fine it is if you want to, but I'm going to run the whole thing again. And I can get a lot more grid markers. There it's at 5. There's ways of indicating the actual density of the grid. Can you all see that grid in the bottom one, class? I'll blow it up a little more. Now I'm going to change this frequency to 5. Watch what happens. Bingo. It's right at 5, isn't it? Now, a couple other things I'm going to show you about windowing here. Before I do anything with the Hamming window or any of these things that start to get rid of the side lobes. What, anybody here have an idea of how we can actually blow this up? Shrink this main width. Do you remember what that main lobe width was in terms of the number of samples for using the rectangular window? Anybody? Very good. 4 pi over the number of samples. Do you remember that? So as the number of samples increase, that window width should decrease. Do you all agree with that? Now we can increase the number of samples 2 ways. We can sample out to a second, but instead of sampling at 1,000 hertz, we could go to 2,000 hertz. Or we could simply lengthen the total number of samples. Instead of 1,000 samples, we could have 2,000. In other words, there's many ways to do it. Are you with me? I'm going to go ahead and do one. I'm going to come here, and I'm going to put this back at 6.5 now. And instead of making this 1,000, I'm going to make 2,000. But I'm going to do one other thing too. I'm not going to run this clear all close a little bit. Let me blow up the original one right there. And now I'm going to rerun this and. Pardon? I'm about to. I went from 1,000 to 2,000. Let's see if it narrows. Matter of fact, let's go overboard. Let's make it 4,000. That way it should be exaggerated how narrow it gets. You follow me? Let's just see. Remember, here's what it looks like. Oh, and I should have left it at 5. But you see how much narrower it is, class? And you can keep on messing with that. Now here's the trade-off. By increasing the length of the window, you've done really two things. Well, now remember, when I'm talking about radar now, when a signal's coming back, I'm sampling it over a very short period of time with a window, and then I'm looking in the frequency domain to see if in fact there's a signature out there. And if there's not, I know there's no target on it. But the longer that window is, the more uncertainty of where target is. Do you follow me? And we would like to know what sometimes it doesn't matter. If you're talking the difference between 10 feet and 100 feet, not a big deal if you're talking of the order of miles. But if you're talking the difference between 1,000 feet and 10,000 feet, and you got something coming at you at Mach 3, and your maximum range is a couple miles, that's a big difference. Now, it's always something you have to worry about the actual problem that you're addressing with the size of these windows. Generally speaking, though, the easiest way to deal with something if you need a narrow window to take a look in the frequency domain, just say there's two targets. I'm just going to tell you where I'm going with this. Without going into the Hamming window or anything, just suppose not only I have one cosine waveform, but I have another cosine waveform next to it showing me a frequency shift. Are you with me? What I'm really trying to do is say this would be the return of a target at where the radar is at 6.5 hertz. Well, if you had a target that's moving fast towards you, right, then this thing's shifted this way, right? Correct? And if in that same, you might say, region, I had a target moving away from you, then there would be a shift this way. Follow me? So you would like this as narrow as possible so you could distinguish what in fact's out there. That's the idea. Without, getting to the point where now you can't tell the range it's at. So there's these trade-offs. Trying to show you everything at once, maybe that's not the best idea, but you're going to see how come all these things are important. Dr. Reese's course really goes into this. Now, we've talked about that was at 4,000. I'm going to put it back to 1,000. Take a look at this waveform one time, and I'm going to show you a few other things. Oh, it works. All right, that was the waveform. Now what I'm going to do on top of this, I'm going to show you what happens with a Hamming window. We could use a Hamming window. Windows are the nice thing about MATLAB, it has all the windows used built in. Right? And I'll show you the waveforms too. So next, I come down here, and this is a it's Hamming, and it can be, I can make it a Hamming window in a second too. So I'm going to go into this thing. And I'll run the whole thing again. Now, what I did was, let me go to the code so you can understand. What I did here is two things. Let me bring this code up, and I'll talk about it. This first part, the subplot 2.1, right here, that's simply the actual original waveform that we're showing there. It's, excuse me, right here, 2.1.1. This is the original waveform in the time domain, or in domain, for the link. This down here is going to be the plot of the DTFT over just the range from 0 to 1,500. In other words, focusing on low frequencies because our targets, because the returns, the cosine waveform, 6.5 hertz. Are you with me on this one, class? And the next thing we're doing is, now we're adding a Hamming window to this. I want to tell you, MATLAB allows you to go ahead and simply, see how I have HAN_win. I'm defining this as a function. And it's simply going to take the number of samples n, and it's going to find the weight of the Hamming window for simple n samples. Remember how they look like a cosine waveform for the Hamming and the actual Hamming window? Are you with me? So it's taking that interval n, and it's multiplying each point in that domain from 0 to n by what would be the Hamming value of the function. And we can put Hamming too. Now when it does that, when we look at these plots, I plotted that one in red. Down here I plot this One other thing too, you see when I have hold on there? I don't wanna go too fast. How many have used hold on before plots? What it does is it doesn't throw a new plot up and get rid of the old plot. It's gonna hold the old plot and just replot on top of it. That's what hold on does. So you can add more and more information to it, and that's what I wanna do. Do you follow me on this thought, class, everybody? So when I do this, hopefully, I'll blow it up. I'm gonna put a grid on here too. I didn't do that. I'll show you a quick way to do this. If you don't want to redo everything, all right, hold on here, I can put grid on. And I can just highlight that. And then it should be F9, but apparently my F9 doesn't work. So that should put a grid on there. Oops. didn't. I don't know if I do this. This should work.
There,
There's a grid on this.
yeah,
What?
it's on.
There's a grid on the bottom plot.
Yeah, but it's, I guess it is, you're right. I should put a more dense grid. I almost don't want to fool with that, but, you all see one thing here that's very obvious. You see how these side lobes out here, that could be problematic, vanish? With a Hamming window, that's a Hamming. We're gonna put a Hamming window on. Hamming's a little better. It gets 43 dB of attenuation in the near side lobe. That's over a factor of 10,000. Hamming window is good. I forgot if it's 39 or 38 dB. It's not quite as good as a Hamming window though. And that's the reason Hamming is used by so many people. And radar signal processing is a big, big deal. And they have spent a lot of time finding optimal windows to do things. Now, what's the downside, by the way, of using a Hamming window or Hamming? Here, I'll put the Hamming on because we talked about it. Here's how tough it is to do, by the way. If I come here, and I just go to my code, you're gonna like this with MATLAB. All these functions. That's Hamming, this is Hamming. I can even change the name there if I want it, but you're not gonna see much difference.
Can you also show how to make the grid more dense?
Sorry?
Can you also show how to make the grid more dense?
Yeah, I will. And I'm going to show you how to look at the help functions too in 1 second if you need help for anything. Because you spend a lot of time in MATLAB looking for ways of doing things you want to do. I'm just telling you that right now. You're going to get your coursework, especially your courses. Dr. New did he ever use anything with Python when you did his course? Well, in the upper level courses, you're going to be using a lot of MATLAB. It's in like EMAG, I know EMAG 2, there's a MATLAB project. In most of the upper level courses, you use MATLAB and Python, or Awkward, if you want to, and you use a lot of it. I'm actually surprised you haven't used a lot of Python or Octave or MATLAB already. Did you use C programming? Were you required to write with C already? For courses here in EE? What course was it?
No, we were required to take some.
What's that?
I only had like.
You had the course. When you had Dr. Irwin's course in the laboratory, did they require you to do PSpice or LT-Spice or anything?
We had to write a program in the lab.
LT-Spice?
No, we use multi-sim.
Multi-sim, all right, these are circuit analysis programs. They're really for bulk or lumped elements like resistors, capacitors, inductors, transmission lines, stuff like this. There are going to be codes you're going to be required to write at the high, and when you get into your junior, senior level courses that are going to be based entirely on MATLAB and possibly Python. And I say Python for a reason, because it's free and it's used for a lot of data mining operations that MATLAB isn't really designed for. I don't use Python, but I'm going to have to, I found out. But everybody's doing it, so I have to learn how to do it, or else I'll be left in the cold. Now, what's the one bad thing about a window like a Hamming window? Somebody alluded to it. The main lobe is wider. It's doubled what the lobe was of the rectangular window, right? That was the bad thing. All right. Now, a couple other things I'm going to show you. So for this, got to tell you, the reason we zero pad also is with a regular, if you have a function, say it's a cosine waveform, and you go ahead and multiply it by a pulse, right? Well, what we really would like to do is have this thing, this pulse go out to infinity, but that's an impractical thing to do with a computer program. So what we do is take the pulse length, and then we zero pad to some very large value. See, the interesting frequency is at 6.5 hertz, right? But I got a sampling frequency of 1,000. That's way more than I need in terms of minimal criteria. But in order to get something and look at the actual waveform, what the frequency spectrum is, I need to use not 1,000 points. I mean, the original sample was 1,000 points. I have to use 100,000. And that's basically what? That's 3 orders of magnitude beyond the actual sample length, if you think about this, right? So what I've done is I got a pulse out there to 1 second, but I've gone all the way out to what? About 100 seconds. Isn't that right, class? So when I go and take a look at it, when I first sample it and transform it, now it's very, very close to a real Fourier transform of an event that went on forever, or a true DTFT that went on forever, if you know what I mean. We're approximating what in fact you'd get with a real DTFT or a real Fourier transform if we adjust for things. And you see it right here. There's one thing I want to tell you that didn't show up well here, or nobody mentioned. Do you notice anything in this one that bothers you just a little bit? Take a careful look at the scales. Can you see them on the vertical axis? What do you notice the vertical axis? Pardon me? I couldn't hear you. What? You notice that 500 value? In fact, what's going on there is that the number of samples is weighing that. We're only showing, let me get this, we're only showing the positive frequencies. We're not showing the negative frequencies in this actual, I'm just making sure I'm not showing negative frequencies. Now, the thing about it is also it's scaled up by a factor of 500. It should be scaled by 1,000 if it was a single-sided, but it's a double-sided transform. It's scaled by half the number of samples. Normally what you have to do is divide this, where I have the DTFT, by a factor of n, and then the peak value would be a half, because you want to scale it right. But there's no scaling in this one, because really what we're looking for is just the evidence of a signal. We're not worried about the scale of that. Y'all see there's a sine wave. I mean, there's something happening at 6.5 hertz. Do y'all agree with that? All right, now, in the thing I asked for Friday, I have 4 different frequencies, don't I? And 4 different weights to each frequency, correct? I'm not going to do that problem for you, but I'm going to show you how you can adjust this to do that problem, all right? Yes? Oh, I hope this is helping you guys, because I can't think of a better way to do it. I wish everybody had MATLAB in front of me. But we don't. So what I'm going to do is this. Here's my original waveform, right? I'm going to go ahead and add both magnitude to it and different frequencies to this. Don't worry, I'm going to send you this code. I'm not going to let you hang it. You don't have to take a picture of it. I promise you I'll send it to you. If you want, I'll send it to you right now, so all the anxiety. How about that? How about I do that for it? I'm going to put it up there because I can see people looking at their cameras. Oh, you won't. I want to make sure I know what to do. You'll forget. I'm like, I'm going to, let's see, Matt, tell me if you can see this on your thing. I hope you can. I'm not taking that down. It's going to stay there. Dr. Baginski's that. All right. Now, what I'm going to do here is show you by adding weight. Now, we're going to mess with the windowing too. All right. We're going to do everything in this. Are you with me? First thing I'm going to do is I want to comment all this out. The way you see how you got all those comments at one? When you highlight the area and hit Control R, it will comment everything. Does anybody here use LaTeX or Tech or any? You know? All right, I'm going to warn you about one other thing too. If you guys are going to be doing scientific work in the future, Word is great for all sorts of documentation the government uses and a lot of the memos, executive summaries and stuff you're going to be writing for your bosses. But technical writing, where you're illustrating a lot of things and you're using a lot of graphical images, and you're gonna have figures that you're gonna have to rotate and shift and get exact. And you're gonna have to do a lot of citations. I would recommend you learn LaTeX, specifically use Tech Studio. Does anybody, have you used Tech Studio, Josh? Do you use LaTeX?
Yeah.
Techniques?
Specifically share like that.
All right, do you use Tech Studio?
No.
I will tell you this, I've used LaTeX. LaTeX is the actual language, it's the program for typesetting. It's being used, and it's used by journals. This is as good as it gets. The thing about it is an engine that does stuff. Now, in order to visualize this, they have tools that show you what you're doing. My favorite is Tech Studios. I've used Techniques. This is specifically to the guys that are going to be doing, if you're going to go on for your graduate degree or you're going to be doing scientific work in a laboratory, and a lot of you will be doing this whether you know it or not, you're going to find out that Word is very good for executive memos, things like this. If you want to create a report with a few sloppy figures and stuff like this, it's fine. For things, if you're going to write technical things, especially manuals or long things like books, LaTeX is so far so much better, you can't even put it in words, in my opinion. So I'm just going to tell you, consider learning that. You heard it here first. You used it, John? You used it? Who else used it? Josh and who else? You used, what do you use it for? You're another guy.
Like at laboratories. Yeah, we used it for circuits.
You use LaTeX for circuits?
You good with
Who
that?
used LaTeX for circuits?
Foundational ones.
Wow, you guys are way up in, you're way ahead of the curve if you've already dabbled in it, because it's going to be, it's used so. This is what I've found. I've been doing this for a long time, over 30 years, consulting and all sorts of stuff. When you're dealing with scientists, journals, people that really know what's going on, it's always LaTeX. It's always going to be tech, LaTeX stuff. If you're dealing with management where you have to distill everything down so they can understand it, because half these people don't understand the way you transfer it, then you write in Word. And I'm just telling you the truth. And if you don't believe me, just talk to some engineers that do really do design work. They're going to say the same thing, that when you deal with management, don't quote me on this, when you deal with people in management, most of the time, you have to dumb it down. They aren't engineers a lot of times, or if they are, they're poor. You have to make it, you have to make them appreciate. I'm telling the truth. I mean, this is not a lie about any of this stuff. It's like in fine arts, if somebody who's in fine arts talking about explaining me to fine artists, then they'd have to dumb it down to me. I don't have an appreciation for a lot of stuff they do. But I'm telling you what you're going to need to do. Now, that said, I'm going to go through, and what I'm going to do is add some more stuff. How about we give this a weight of 2, and let's add a few more. Let's put some frequencies up here. I got F naught there. How about F1 equal to 8 hertz, right? 8, and then call it F2 equal to 10 hertz. And now, let's go here, and I'm going to change the weights on this. I got 2, how about make this 4, and make this 1. And then make this F1, right there, and make this F2. Now these are close together, right? So we should see some overlap. We're only taking a regular window. We're not doing anything, we got Hamming window or anything else. You with me? So let's see what it looks like. I haven't done this one yet. All right, it looks pretty horrible. I mean, if you were a radar operator and that was a snapshot, how many targets do I have? Take a guess. Too many. There's something out there, fire countermeasure, whatever. I don't know what's out there. I mean, that's just disgusting. So now, what happens if we start? How do you want to start cleaning it up first? What's one way before we do windowing? Anybody? What did I tell you? What
Increase
narrows
the
it?
number of samples.
Yeah, I think maybe we could see something, increase the number of samples. We're still gonna have a problem. I'm gonna go from 1,000 to 2,000, just to see. I'm not sure. Well, It's starting to look more like I got discrete signals. I said 1 at 10, didn't I? Didn't I have a frequency of 10?
Yes.
Doesn't look like it's at 10, does it? Let's see. 10, 8, anybody have a reason, idea why that's probably off a little?
The target's moving.
That's clever, no. What you're getting the effect of the two cosines being so close together, you're actually, if you look at this, because I've got a short, I mean, if you look at this is a very short, relatively short window. I'm effectively skewing that frequency by the cosine waveform that is at 6.5, I believe. 6.5 levels would be 13, I think, but let me show you some other things. Now what I'm going to do, instead of 2,000, let's go to 4,000, see what happens, okay? Sure is. Let me see this, make sure I didn't do something stupid here.
Try changing it just to see what happens, maybe 20 or 15.
Now I'll change the weight on this one.
Okay.
Make that weight 10. And F2 is a 10, isn't it?
Mhm.
Are they kind of messing with each other with the blades? Would they be like messing with each other with the blades? They want some be greater than this,
All these things are at separate frequencies, but because I have to play with this a little, what I'm going to do is this. I'm going to take this whole thing right here, copy it. I'm going to put it down here. Then I'm going to comment the top one off. And I'm going to get rid of everything but the last one. I want to see something. Oh, you know why? Because of this, I didn't put N here. That's the reason. It should be by N right here. Let's see if that does it. Oh, we're changing too much at once. Let that be 1,000. Let this be N. I'm about out of time, am I not? Yeah, it's right at 10 now. I'll explain what went on. I have, the window N is the scale you have to actually adjust to when I have the length of the window N times the actual, this N times this, but now the actual number of samples here is still going to be the same. I'm running out of time on this one. Let me just do these three with a hammy window. Leave it as 1,000. Hold on. Let me comment this out. Hang on, man. Let me just put this with a hammy window. First, I want to make sure that they all be at the right place. Well, let me take this one down a bit so it looks real garbage. Yeah, now the hammy window. Control T gets rid of all those comments, by the way.
Do you want to use Hanning or Hamming?
I'm gonna make this at 10. I'm gonna make this at 15. I want, trying to get some more spread on this thing. Alright, it's still not showing, I'm only got, what I'm showing you is just the lower frequencies, but that windowing function, you're gonna find, when I increase the length of the window, it's at 1,000. When I make that 4,000, what you're gonna see is the Hamming window give you very distinct, it'll clearly show where those frequency components are, and the others won't if you get several frequencies close to one another. That's what your thing is going to examine for Friday. Remember, you got 3 frequencies, I think, or 3 or 4 cosine waveforms? Y'all look at that yet? And you should be able to do that easily. And I've got the Hamming window there. Use the Hamming window. There's one other window that you can use that'll take you down like 58 dB below there, but it widens the thing to 12 pi over the number of samples. Ours is 8 pi, the main beam. And anyway, you're going to play with that for Friday, okay? If you have questions, yes?
I don't see the 3.
Isn't that up there?